Hello and welcome back to episode 4 of Stats with Mats. Happy Monday. This week we are going to be covering ANOVA. Now, in my opinion, and based on my experiences previously teaching this class, ANOVA, which stands for Analysis of Variance, is usually the most difficult topic that we cover all semester. So buckle up for this week. While this is difficult and takes some time and practice to master, I have no doubt that with the requisite time and with the requisite level of care that we'll all absolutely be able to do it. So that my agenda for this week is simple. First, I want to spend today, this entire lecture today is going to be dedicated to the idea behind ANOVA and getting comfortable with the steps that we use to conduct an ANOVA test. We will not actually calculate an ANOVA formula and problem and get to an answer until Wednesday. Okay, so think of this as kind of a two-part process. Today, I really want to tackle and spend a lot of time on the idea behind ANOVA. When it comes to the steps and knowing what to do, that's 90% of the battle here, is knowing what to do, in what order to do it, and why we're trying to accomplish things that way. Okay, so that's going to be today's class is setting up an ANOVA problem, and our class on Wednesday is going to be actually answering that ANOVA problem. Before I get to my material, today's dumb movie comment of the day is about the Rocky franchise. I saw Rocky 2 on TV last night, actually. Watched a decent portion of it. Rocky is all of the Rockies are great movies, and there is a lot of discussion among people, especially males my age, as to what the best Rocky movie is. And a lot of people say Rocky 1, sometimes people say Rocky 2 because that's when he actually wins the title. In my opinion, thinking about the movies as separate entities misses the point. And here's how I would think of it. If Rocky was an actual boxer, what would have been his most memorable fight? And that has an easy answer. It would have to be when he fought the Russian, right? It would have to be the fight against Ivan Drago in Moscow on Christmas Day, when Rocky defeats the master heavyweight Ivan Drago, gets the Soviet crowd to root for him, and inadvertently ends the Cold War as well. And it's hard to believe that any fight previously in Rocky's career would have been remembered in the same way as that one. So because Rocky IV would have been his most memorable fight, that by extension to me becomes the best Rocky movie. All right, let's get to ANOVA. As I said previously, ANOVA stands for Analysis of Variance. This is a hypothesis test that we conduct in a situation where we have an interval level dependent variable, right, an outcome that we want to test. And we have a categorical variable, which can be either nominal or ordinal, that has 3 or more categories. So the logic here is kind of similar to what we're operating with on a t-test, where you were doing a comparison of means. But for a t-test, we could only use a variable that had 2 means, 2 groups. That's it. So we looked at males and females in our homework. We could have looked at, say, undergraduates and underclassmen and upperclassmen, for example. Here, we still have the means that we care about. It's still an interval level mean that we want to test. But we want to look for differences now across more than just those 2 categories, because a great deal of the world and social life is just not reducible to 2 and only 2 categories. So let's take a look at the example that we have here. This is the example we're going to spend the next 2 days working through. I want to understand, let's say I have a hypothesis that homicide rates differ across the core economic base of a city. So let's look at the table here. I have murder rates per 100,000 people in the population, and I have 3 groups of cities. 1, manufacturing, think a place like Pittsburgh or Detroit or Cleveland. I have service, think a place like New York or Boston. And I have government, although you can't quite see that here. I will move my ugly face here. Government, and there think like I don't know, Salt Lake City, for example, Washington, D.C., Sacramento, Albany, New York, whatever. And I want to understand what's up with the homicide rates. Do we find a pattern within the specific groups of cities? So the way I encourage you to think of this is, if you tally up the means here, I have 24 different observations, all with their own murder rate. And then I have 3 grouping variables, each with 8 cities in them. So while I have a sample here of 24, I can also conceptualize this as 3 separate samples of 8 cities each. 8 manufacturing, 8 service, and 8 government cities. So this is where we take a step beyond the t-test. Instead of 2 hypothetical populations, we now have 3 hypothetical populations: the population of manufacturing cities, the population of service sector cities, and the population of government cities. Okay, so the equation that we're going to work through here, and there are more than a few steps to this, will serve to partition how much variance exists between the groups and how much variance exists within the groups. If that makes no sense right now, don't close the video and we'll work through it, and hopefully it will make sense by the end of it. But that's the point here. We want to understand, is the variation being driven within the group or between the group? If it's being driven between the group, that's what we need to find in order to reject the null hypothesis. If it's all happening within the group, then there might be a lot of variation, but it will not appear at that point to be driven by group level differences. So what the equation will ask us to do is to sum all of the variance, all of the variation that exists within this data set and partition it. We have to decide how much is happening within the group and how much is happening between the groups. And that will allow us to answer the question that we care about here. Okay, so what I want you to do first is examine what's known as group means. I have a sample of 24 cities, and once I break that down by grouping variable, which is the type of city, the economic function of the city, I can see that the group mean for manufacturing cities is 8.58. I can see that the group mean for service sector cities is 5.6. And I can see that the group mean for governmental cities is 5.95. So instead of just having one mean that I want to compare to a predetermined variable, or 2 means from 2 samples that I want to compare to one another, I'm now operating with 3 group level means. And so our 24 observations here, split across 3 groups, produces 3 group level means: 8.58, 5.60, and 5.95. But if you're thinking ahead here a little bit, you might have realized that we actually have a 4th mean that can be calculated here. It's the mean of every city regardless of the group, okay? And that's going to be called the grand mean. So if I have an ANOVA problem with 3 groups, that implies I have 4 means that I need to be working with here. The group means refers to the mean of each specific group. So the group mean for manufacturing, or put another way, X bar 1 would be 8.58 for manufacturing, X bar 2 would be 5.6 for service cities, and X bar 3 would be 5.95 for your governmental cities. And then if I add up all 24 of those observations that you see in the table and take the average, I will then get the grand mean, which works out to 6.71. Although, here's something that's pretty cool. Maybe some of you realize this intuitively, others may not. I admit this is not something I realized intuitively until it was told to me many years ago. If I add up all 24 observations here and divide by 24, that will get me the average of 6.71. However, if I add 8.58 to 5.6 to 5.95, and then I divide that by 3, that will also get me the same identical grand mean of 6.71. Pretty cool. So these are the means that I'm working with here. There's a couple of questions that we're going to need to answer. First, how much does each manufacturing city's mean or rate differ from that group mean, right? How different is 4.3 from 8.58, just going down the manufacturing column here? How different is 2.8 from 8.58? How different is 12.3 from 8.58, and so on and so forth. And I will need to do that for every observation in the data set. I will also need to understand how different is each group mean from the overall grand mean. So how different is 8.58 from the grand mean of 6.71? How different is the group mean of 5.6 from the grand mean of 6.71? I hope we're getting it so far. That's all I can say. I really hope so. Okay, so in other words, what we're really doing, throwing numbers on it thus far, but what we're really doing is setting up two types of hypotheses. The null hypothesis here that is implied by what I've been saying is that the economic base is not associated with the murder rates. That is to say, the null hypothesis for any ANOVA is that there is no difference, no significant difference across the grouping variable that you have here. That is to say that while each city might have a slightly different rate from the grand mean, the group means don't significantly differ from that from what that grand mean actually is. And so what that would mean then is any variation you see in the data set would be due to within group differences. Expressed mathematically, I might say that mu of manufacturing equals mu of service sector equals mu of government equals mu of total, where mu total refers to the grand mean. That's the null. If that were the case, then the grouping variable does not matter. And any type of variation that we observe in murder rates is just due to within group, is just due to what's going on within the group, not between the group. What we want to find in order to reject the null hypothesis and say, yes, the city's industry matters is the alternate hypothesis. And that's that the economic base is associated with the murder rates. So while the math is going to get pretty difficult here, the hypothesis should be very easy. The null is always that the grouping variable doesn't matter, and the alternate is always the grouping variable does matter. You don't have to worry about tails anymore. You don't have to worry about directions. It's just a matter of between group differences or within group differences. And so if we were to find support for H1, if we were to reject the null hypothesis, then variation here is driven by between group differences, or mu of M does not equal mu of S, does not equal mu of G, does not equal mu total. Put another way, the rate that we see in manufacturing cities is different from the rate that we see in service cities, which is also different from the rate that we see in governmental cities, which in its totality is different from the rate that we observe within all cities, regardless of group. If there's a difference there with any one of those, it will trigger a rejection of the null hypothesis. Okay, so moving on then, ANOVA is all about variation from the mean. Therefore, it's going to bring back an alteration of a formula we're all pretty friendly with at this point. If we want to know how much variation exists between the rates of these cities and also within the rates of these cities, we have a formula for that. We are going to be making use of the sum of squares. You will remember what we did at the time that we were learning standard deviation. The variance of any data set, of any variable, is defined as the summation of xi minus x bar squared over n minus 1 for a sample. So this is not the formula we're going to be using. This is the formula's logic that we are going to be adapting in order to make use of ANOVA. So what did we do here? We took each observation of xi, subtracted from it the mean, squared it to get rid of the negatives, and divided by n minus 1, the sample size reduced by 1 in order to inflate the variance. And so what that's doing is it's giving you a sense of how different, how much sum of squared variation there was from the mean, or from between the mean and any one observation within the data set. That is essentially what we're going to be doing here, okay? And if we find the types of associations we find are going to be what we need to make decisions about null hypotheses versus alternate hypotheses. So what if we had a perfect association? Perfect association would be a situation where within each category of the independent variable, that is the city's type, all values are exactly the same within the group, but between the categories, the mean values would be different. So put another way, I would see the same number for every observation within a group, but I would see a different group mean from anything else. That would tell me that all variation is being driven between the groups. So to put that in other words, if you need another sort of go with it, go through it, the mean murder rates are different between each type of city, but all cities would have the exact same rate. Now, for those of us that are visual learners, it might be helpful to take a glance at what perfect association would look like. You will remember that the grand mean here is 6.71. So this is a situation where all variation is driven by group level differences. Here, I have 8 manufacturing cities, and every single one of them has a murder rate of 8.58. Therefore, X bar 1, the first group mean, is going to be 8.58. There is absolutely no difference between individual observations and the group mean. But that group mean of 8.58 does differ from the group mean of service sector cities, which is 5.6. However, within that second group, all cities have the exact same value. So you will notice here, for this situation, this is hypothetical, but this would be a perfect ANOVA relationship. No variation whatsoever within the group. All variation is happening between the groups. Now, as for what absolutely no association would look like, consider this. So here, what has changed? Now I have a lot of variation within the group. 8.58 is different from 2.3, is different from 5.63, is different from 8.5, or 8.4, pardon me, is different from 3.4, so on and so forth. But those 8 observations in the manufacturing category, they all sum and are divided by 8 to get to 6.71. So put another way, the group mean for manufacturing is 6.71. What about the group mean for my service sector cities? Okay, well, I see a bunch of different numbers there, but the group mean now is still 6.71. And the group mean for government cities, a lot of variation within that group, but the group mean is still 6.71. So put another way, you can see that while there's a ton of variation in this data set, there's a lot of different numbers and different values in here. It's all just noise. It's all happening within the group, and there's absolutely no pattern between the groups. How do we know there's no pattern between the groups here? Well, the manufacturing group mean is identical to the service group mean, is identical to the government group mean, which is identical to the grand mean of 6.71. That's the value for all 4 of your means here. So to go backwards just 1 second here. If this is what I found in theory, this would allow me to reject the null hypothesis and say, yes, there is a significant difference in murder rates across the grouping variable of city's economic base. But if I see this situation, I would say, no, I fail to reject the null hypothesis because while there is a lot of variation, it's just noise. It's all happening within the group, and the grouping variable itself has no effect on the outcome. So let's get comfortable with some notation here because they're going to show up frequently in the formulas that you have access to. I would like you, as we have done over and over again, let X stand for an observation. But we have to get a little more specific than that because remember, we have 24 cities here, but they're set across 3 different groups: manufacturing, service, and government. So let I stand for the row and let K stand for the grouping variable. So if I said XIK, that is referring to the value in the ith row of the kth column. Now, it sounds a little weird, but again, if I go back to the table that we had on the very first or second slide, let me go back just to get one here. In the data that we're operating with here, let's look at the very first rate in the manufacturing group. So that is the first observation in the first column. That would be X11. If I wanted to look at this service sector mean of 5.1, that is now in the second group, but it is the first number, first observation within the group. So that would be X12, and so on and so forth. Then X bar 1 is going to stand for the mean of group 1. X bar 2 will be the mean of group 2. X bar 3 will be the mean of group 3. Now, in our problem here, in our situation, we do not have a secondary, we don't have a 4th and 5th and a 6th group, but there's no reason why we couldn't. We could have as many groups as we wanted here, and that would be just fine. So if I had a 4th group, let's say I took tourism cities, for example, that would be X bar 4 for that group mean. And then finally, X bar total will refer to the grand mean across, again, all rows and all categories, just every observation summed and divided by the sample size. And those, it's the second part of that, X bar 1, X bar 2, X bar 3, and X bar total, that are going to be most important to utilizing the formula correctly. Because if you start subtracting the wrong mean from the wrong thing, like that will very likely lead you to the wrong answer. So the partition variance then, we, again, as I have been saying, I really want to reinforce and drive this point home, we want to be recognizing that there's 2 forms of variation in our data set. There is the extent to which XIK differs from its group mean of X bar K. Put another way, take that first observation in the manufacturing group. How much is that value different from the group mean of 8.58? So XIK, each observation in the group, how different is it from its group mean? That's known as the difference within the category. And we will do it for every observation within the group. Secondly, we have another type of variance or variation. And that's the extent to which the group mean X bar IK differs from the grand mean. Actually, let me just get rid of it. This should just read X bar K. I'm sorry. All right, let's start that over. So what is the extent to which the group mean X bar K differs from the grand mean? So again, going back to our manufacturing group there, how different is X bar 1 of 8, which is 8.58, from X bar total, the grand mean, which I remember being 6.71. That is known as the difference between the categories. Expressing that mathematically will run as follows. The summation of XIK minus X bar total squared equals the summation of XIK minus X bar K squared plus the summation of X bar K minus X bar total squared. Total variation, within group variation, and between group variation. So step one, I would like to introduce a second, a new first step in our hypothesis test, and that will be don't panic. Let's go through this in order. In order to understand total variation, we will need to take every individual value of X, subtract its group mean from it, square it to get rid of the negatives, and then sum it to understand the total variation within the group. And that will help us understand the difference within the categories. And we can then add that to the summation of X bar K, that is the group mean minus the grand mean squared, once again, to get rid of the negatives. You add those two together, and that's the total variation in the data set, partitioned into within group variation and between group variation. Okay? In other words, sum of squares total, the total sum of squared variation equals the within group sum of squared variation plus the between group sum of squared variation. I'll let that sink in for a second and let you guys finish writing if you need to keep going through this. In other words, within group sum of squares is the sum of squared deviation of every raw score from its group mean. And we will need to do that for all 24 cities within our data set. Meanwhile, between group sum of squares is the sum of squared deviation of every group mean from the grand mean. Now, of these two, calculating within group sum of squares is by far the most time consuming. So that when we actually get around to calculating it, that will be where we spend the most of our time. Like that's going to just take the most amount of time. The rest of it actually flows pretty easily. You just have to make sure you're using the right numbers and make sure you haven't made any type of careless errors. Now, why does this matter? I keep prattling on about within group variation, between group variation, blah, 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 blah. Why does this matter? Well, it matters because, again, bring it full circle here. If most of the sum of squared total variation, if a great deal of all of the total variation is attributable to within group variation, then there is no association between the IV and the DV. And what I mean by that is the independent variable and the dependent variable. The independent variable is the thing that is being hypothesized to affect or to influence the variable that you care about, known as the dependent variable. So in our formula here, the city's murder rates, that's the dependent variable. That's the thing we really care about understanding. And we are hypothesizing that the city's economic base has an effect upon what those murder rates are. So the city's economic base is the independent variable. It's the thing that does the influencing. The dependent variable is the thing that gets influenced. So I hope this is starting to solidify here. If you find that almost all of the total variation is due to what's happening within the groups, then the groups themselves don't really matter when compared to each other. There just wouldn't be much of a difference between manufacturing, service, and government sector cities. But if you find that between the groups, that's driving the majority of the variation, then that will tell you that there is a very clear association between the independent variable and the dependent variable, okay? So let's revisit that. I realize I keep beating this into the ground, but that's because since it is so easy to make a mistake with the ANOVA formula, and because it's so easy to make a careless math error, I have made countless of them in my life, making sure we have a core understanding of the idea is almost like it's a guard against making those careless and silly mistakes. It makes it less likely. So again, this is what perfect no association looked like. There's clearly differences in the rates, but everything is happening within the group. While 8.58 differs from 2.3, differs from 5.63, differs from 8.4, and so on down the line, even though there's all this variation within the group mean of 6.71 does not differ from the service sector group mean of 6.71, which does not differ from the government group mean of 6.71. Total those up, and none of it is different from the grand mean of 6.71. But if most of SS total, all of the variation in the data set is being driven by variation between these categories, the only difference I see here is 8.58 is different from 5.6, is different from 5.95. No variation within the groups, all variation between the groups. Now I'll pause here for 1 second. Like this is a hypothetical example. I didn't actually find 8 manufacturing cities all with these homicide rates. But if you Google me and find any one of my articles, you will likely find a one-way ANOVA that I have conducted and published on in anticipation of running a regression at a later point. And that's because I do all this cross-national analysis. And so I will often have a dependent variable, and I need to understand, in order to construct my model, construct my equation, whether or not there are group level differences. So if I just think about using Europe as an example, because that's what most of my articles are about, is there something that the people living in Germany have in common with each other that makes them different from the people living in France? Yes, of course. These people live in Germany and these people live in France. So put another way, let's say I have a sample of Europeans across 20 different countries. I want to know whether the values of my independent variable, which recently has been something like protest participation, differs across the group mean in Germany, the group mean in France, the group mean in the Netherlands, the group mean in Spain, and so on and so forth down the line. So be aware, these techniques I am teaching you, you can publish with these techniques. I've done it. And that's why when you successfully make it through this course, often grad programs will release you from your entry-level stats requirement if you're doing anything in the social sciences by virtue of just taking a look at this syllabus. So do not throw that away. So anyway, now for the moment you have all been waiting for, how do we actually do the math on this? When it comes time to actually conduct an ANOVA test, you're going to want to do a 7-step process. 7 steps? Was I serious? Yeah, no, I am serious. And that's why take care to break down the formula. So at this point, it would very much help you to have your stats packet out and to go and look at the page where you see the ANOVA formula, because I'm going to be breaking this down in the order that you're going to want to do it. Step 1, easy. Calculate the group means and the grand mean. That's going to be the first thing that you need. You cannot go further if you're not aware what the group means and the grand mean is. So in an ANOVA problem where you have 3 groups, you must calculate 4 means. The group mean for each of the 3 groups and the grand mean across all 3 groups. Once I have that, it's time to start partitioning variance. So step 5.2, calculate the sum of squares within the group. And in order to do that, we must use the group mean. So take a look at the formula here. The sum of squares within is the summation of xik minus x bar k squared. So let's actually start in the middle of that equation, as the order of operations would tell us to. So I take xik, which is one observation in that group, and I subtract from it the group mean. So let's just say I take the very first manufacturing homicide rate, subtract from it the group mean for manufacturing cities. I then square that to get rid of any negatives that may or may not be there, and sum across all 8 cities. But I'm not done there. So if you're wondering what the summation of the summation is referring to, I need to take the summation of all 8 sum of squared differences for manufacturing cities, and then I need to do the same thing for my service sector cities, and then I need to do the same thing for my governmental cities. So I'm doing the summation for each of the 3 groups and then doing a summation of all 3 of those groups. I will repeat that to make sure it's clear. I take the sum of squared deviation from the group mean for the first group, do it again for the second group, do it again for the third group, and then add them all together. And that is the sum of squared deviation within the group. And that's by far the most time-consuming part of it, because once we get to the next section of sum of squares between the groups, now we can make use of the fact that we know what the grand mean is. So I will now, again, I'm going to start in the middle of this equation. I will take my first group mean. I will then subtract it from the, I will then subtract the grand mean from it. I will square it to get rid of any pesky negatives, and then I will multiply by the group size. So put another way, what was my first, let's think about what the table looked like here. My first group was manufacturing cities. The group mean there, X bar K, for manufacturing was 8.58. So I will do 8.58 minus the grand mean of 6.71 squared and then multiplied by the group size, which in this case is 8. Do not forget to do that NK, right? The size of the group. You must multiply in order to inflate it out to how many observations are actually within the group. And then you take the summation. So I will need to do that for all 3 of my groups. So the second group mean is 5.6, I believe. So the way this would unfold is as follows. 5.6 minus 6.71 squared times 8. And then my final group of 5.95 in the governmental cities, 5.95 minus 6.71 squared times 8. All of your groups have the same size here, so NK will always equal 8. And then I sum those 3 values together, and that gives me the sum of squares, a squared deviation between the groups. So you can see I need to do, for sum of squares within, 24 different little math problems. For sum of squares between, I only have to do 3, because that's how many groups I have. If I had 4, I would have to do 4. Okay, so now, continuing my steps, what comes next? Step 5.4, calculate your degrees of freedom within and between. This is not terribly difficult, and in fact, since you'll essentially have this already created already for you, because you will need to, in step 4, where you identify the critical region of ANOVA, you will need to have your degrees of freedom, obviously, to look up the table there. So the degrees of freedom between is K minus 1. Remember what K is? That's the number of groups that you have. How many groups? 3. So degrees of freedom between 3 minus 1, which equals 2. And we'll need a second DF, which is known as degrees of freedom within the group. That is N, the total sample size, right? Don't forget about group size for a second. N here refers to all observations, which in our problem is 24. Minus K, the number of groups. Okay, so 24 minus 3 equals 21. So our degrees of freedom will be 2, 21. Why do we need those degrees of freedom? Because that is how we calculate what's known as mean squares. We've already calculated the sum of squares, but now we need to normalize that by the number of groups and the number of observations. So to calculate mean squares within, I take that sum of squared deviation within the group that I calculated previously and simply divide it by n minus k, the degrees of freedom within the group. Now, hopefully you see where this is going. If I had to calculate mean squares within, the next step here is going to be calculating mean squares between the groups. So that is the sum of squared between the group divided by the degrees of freedom between. So I take that number, whatever that summation number that I calculated on the previous slide was, because we haven't actually done the math yet, but I take that first, and then I divide that by the degrees of freedom between the group, k minus 1. So that would be divided by 2 here, whereas mean squares within would be the numerator divided by 21. Are we done yet? Oh my God, I wish. Nope, still a couple more things to do. Step 5.7 is calculating f, but if you've gotten this far, now it's just a really simple equation. Calculating the F test. The F statistic is what ANOVA's all been building towards. Not the T, not the Z anymore, the F distribution. That is simply mean squares between divided by mean squares within. That F that you get will be compared to the critical F, which next time I will show you how to look up. And if that number is greater than what you saw on the critical statistic, if the number that you look up on the table that we'll do next time, you will reject the null hypothesis, and you will say that yes, most of the variation here is being driven between the groups. Within groups, people are similar. Between the groups, rates are very, very different. Or put another way, what we're doing here is creating a ratio of the variance between to the variance within. If this value is very high, if we calculate a very large observed F, then that would mean the variance between is much, much larger than the variance within. If we get a very small number, it would mean that the variance within is much, much larger than the variance between. To reject the null hypothesis for ANOVA, we will have to find the majority of our variation being driven between the groups. So I hope that was not terribly overwhelming. We're actually going to get our hands dirty with this formula next time, okay? So if you are completely lost, I would suggest watching the video again. If you feel like you get the logic, you're probably good to go to at least try the formula, because as with any of these things, the first time you learn it, it's not always so clear. This first time you do it, it starts to get a little more clear. And the second time you do it, that's when you can really start to get comfortable with the process and get comfortable with the problem. So I will be creating a video to work through this formula, work through this problem of the city's murder rates, and to work through the ANOVA formula. And then there'll be a homework. There will be a homework where you have to do an ANOVA on your own. So I wish you good luck over the next couple days. When I see you again, it will be Wednesday. Good luck and Godspeed. Take care.